All right, so we've covered all of the quadratic sorts now, and the next phase that we're going to move into is what are called, maybe you could call them like the divide and conquer style sorts. And the way that we're going to introduce it is we're going to start with a hopefully somewhat intuitive idea, an intuitive example. So we have the homework prioritization problem. And the idea is that you have a pile of calc homework and a pile of computer science homework. And you sort of, these piles are each individually sorted. So, 224 is the due date here, then 225, then 227. And over here, it would be like maybe 225, and then 226, and then 228, and so on. And because you have so many assignments, the thought is, well, what if we could make this into one big pile of homework where we always know which assignment is due next because it's on the top. So we would sort of start here in both piles. And first we see that CS has the earliest homework, so we'd put that down, put down the 224 CS homework. Then we'd go on to the next here. And we see that it's actually the same due date as 225, but I guess it doesn't matter which order they go in, but we can put that down next. So 225 CS. And then we'll look at this one. And we see with 227 that calc homework is actually now higher in the priority. So we would move over to the calc homework list and we'd put down our 225 calc homework. Then we'd move on to 226, comparing that to the 227 homework, and we see that that is more recent or due sooner. So we'll put 226 calc. And then we go to the 228, and we see that that is due after our current position, the CS homework. So now we move back over to the CS stack. And so 227 CS. And then 227 CS. I didn't actually write out. We'll say this is the last homework in the CS stack. Because it's the last homework, we'll move back over to the calc homework and put our 228 calc to finish this off. So we're actually keeping track of positions in each stack independently. And so we'll do this problem in class, but thinking about how to write pseudocode to go through sort of both lists at the same time and only sometimes increment the index is going to be the big challenge of this merge function we will write. And okay, that's great. But one question we might ask is, how can we use this in the real world? And well, I feel like maybe this example is a little bit more real than the example I'm about to show you, because this is like related to your lives. But if we want to use it in sorting, how can we take advantage of this? And so I have a little data set that I've been using. It's 50, 30, 60, 40, 20. And the idea is that every set of data is going to have some small parts of it that are already sorted. We can call them like runs or something. So like I see 30, 60 right there. That's already sorted. It's a run. And I don't actually see that many other runs. But if an element is just on its own, it's kind of like a run of length 1. So if we went through and identified all the runs, we could say, okay, 50 is the start of a run, and then we see 30, and 30 is less than 50, so that's the end of the run. Our next run starts with 30, it goes 30, 60, and then we get to 40, and 40 is less than 60, so that's the end of our run. Then we start at 40, see 20 next, and 20 is less than 40, so that's the end of our run, and we finish it off with a run of 20. And now we have this nice sort of merge algorithm. And we have some runs. So we can actually merge each of these runs. So 30 is less than 50. So we'll put it down first, and then we'll move to 60. We'll see that 60 is greater than 50. So we'll go over to the other array and put down 50. And we're out elements here, so we'll move back to the other run, and we'll put down 60. So now we have merged this run into one big run. And then we have two more runs to handle, 40 and 20. So in order to insert, well, it's not sort, it's, oh my God, I can't speak. It's not inserting. In order to merge the run of 40 and the run of 30, 50, 60, we will start with the smallest element, put down 30, and increase our counter. We see that 50 is now greater than 40. So we'll move over to the right-hand run, put down 40. We're out of elements here, so we'll move back and put the rest of the elements. Okay, and now we have a run 30, 40, 50, 60, and a run of 20. And so we see that 20 is the smallest element, so we'll put it back here. And then we will put the rest of these runs, because the rest of the elements in the left-hand run, because we are out of elements on the right-hand side. And so one thing I kind of want to draw your attention to is I feel like we did the same thing twice with 40 and 20. We had this really long run, and we kind of just we basically put one element down and then just like moved all the other elements. So the actual merge process, we really didn't gain that much. We did a lot of work that was essentially just keeping the elements in the same order. And so I want to compare what I just showed you with an alternate way of doing it. So we would still do this first step where we merge the first two runs, but 30, 50, 60 is still a run we have, and then 40, 20 are still two runs. What if instead of merging 40 into the run 30, 50, 60, we tried to merge it with a run of a similar size, so with 20. So we would see 20 is the smallest element, so we'll put that down first. We exhaust that run, so we put 40 now, and that run is exhausted. And now we have a run of 30, 50, 60. And I just want to point out, merging 20 and 40, it took like very little work compared to it took a lot of work to merge 40 into 30, 50, 60 and 20 into the, the 4-digit long run, 4-number long run. But merging these two small runs was easy. Now we have these two similarly sized runs, and now I think it makes a bit more sense to merge them together, right? So 20 starts us out as the smallest element. So we move over to 40 now, and we see that 40 is greater than 30. So we move over to the array there, put down 30, see that 50 is greater than 40. So move back, put 40 down. This array is exhausted. So now we'll move over to the other array, 50, 60. And now our array is sorted. So I imagine programming this sounds like a pretty daunting task, especially because I didn't do a great job of like saying we're going back and forth, like between the two arrays. That's why I think it's important to sort of decompose this problem by making a merge function that works really well. And then you just call the merge function when you're actually programming it. The other approach I want to show you, or sort of what I want to show you, is how this problem sort of looks when you draw it out spatially. So these are our runs initially, and then we end up with sort of this tree structure as we create the merges. as we merge each run. See, and the example that I've shown you is called bottom up merge sort, because we start with sort of the individual elements, and we start by finding those individual runs. But there's another variant that sort of that cares about how we get these runs in the first place, and that's top-down merge sort. So instead of going through the list and finding these runs and putting them together iteratively, we can use a recursive style of merge sorting. So if I have 50, 30, 60, 40, 20, the idea is first to create runs. We know every single digit is a run, and we know that we like to merge together runs that are of a similar size. So one way we can do that is we can divide the list in half and then call merge sort on each half of the list. So we're sort of breaking this list into 30, 50, 30, 60, and 40 and 20. And then we divide each of these lists in half. And I'm just trying to show sort of the tree structures that we get when we do something like this. Okay, great. And now we've actually created, we would have to do it once more here. But we've actually created a whole bunch of runs in a recursive style. So I'll just draw those. Now that we have these runs, we can put them back together again. So now we would end up with 30, 50. And then we would combine, I guess the best way to show this is to draw that 60 there. And now that's a run, that's a run. And then when we merge them, we will get 30, 50, 60. And now that's a run. And then we go over to the other side of the recursion tree, 40, 20. Just gonna draw them so they're on sort of the same level. And then we merge them, and then we get 20, 40. And that's a run. And now we can put these two runs together and use our merge algorithm. And what's nice about this top-down approach is that when we actually implement it in code, we'll be able to use recursion. So our solution is going to be like 5 lines long, which will not be the case with the iterative bottom. I don't know why it's not called bottom down. It's called bottom up, but bottom down or bottom up approach, basically using the individual elements to build our runs. So 20, 30, 40, 50, 60 is this top-down approach. And it's top-down because we start with the whole array, then we break it up to create our runs. Bottom up is called such because we start with sort of the elements from left to right, and we're just like finding runs, and we're sort of merging them as they come up. And yeah, that's the basics behind merge sort. I think trying to implement it will definitely teach you a lot because you'll have to draw tree structures like this. But merge sort's actually super fast compared to the quadratic sorts. And we'll talk more about how to analyze the big O of merge sort in class. But good luck and have fun with this assignment.